that and that coefficient matrix is nothing but the systems that is basically the systems behavior will be further unfold by the fact that if you calculate the eigenvalue of that matrix, then you will understand that what are the different natures, and if it could be real number, it could be imaginary number, or other not imaginary exactly, the complex number, it could be imaginary number as well. So based on that we can see that whether the evaluations or whether the state variables after starting from that initial conditions, whether it will again go to a different it will go to a different steady point conditions, or asymptotically stable, or it is sustained oscillations, or it is basically expanding, like it is blowing up. So the kind of those conditions where thermal runaway. So different situations may arise. So that is why I will give you the assignment, just one question, which is basically the formation of propylene glycol. So that is an industrial chemical compound which is basically present in several this daily needs. For example, this it's basically a component that is used for moisturizing the antiseptic cream or several of the daily products that we use. So propylene glycol is basically formed by hydrolysis of propylene oxide. So that actually is carried out in non-isothermal mode and in a CSTR. So most of the pharmaceutical or intermediate chemical compounds, they are produced in continuous mode and in a start tank reactor, right? So you must be aware of the conditions on which you have to run the reactor. So that is why this particular topic was very important. Is important, and you must do that assignment problem so that you will have a better understanding. Okay, any questions further if you have on this reactor part, or at least the steady multiple steady state and the stability of steady states that we discussed? Okay, so if not, then let me give one more example, and then we will move to different topics. So here we will not derive like we derived in case of, or at least we elaborated our discussions based on the CSTR. But here basically we are trying to understand the distillation column, the behavior, and by starting it at unsteady mode, and how it is going to reach the steady state point. So basically, if you just consider this distillation column as a case where you will also have a similar understanding that we had made in the reactor case, is that we have to also identify where is that source of nonlinearity, right? Where is the source of nonlinearity in a distillation column? Because when we design a distillation column, we design at steady state conditions, right? So we write the overall mole balance and then species balance across each tray, then at reboiler section, then at condenser, reflux drum. So all the points we write the steady state balance equations, right? So consider it is not at steady state. We probably had some perturbations or from that steady state point. So there are some transient phenomena that we have to monitor, that we have to understand, and that transient phenomena is basically again whether that with the deviation variable, the change in deviation variable, whether it again falls back to the previous steady state point or it goes further away. So the similar situations may arise here. Now here the number of equations will be more, right? In case of CSTR, there was no gradient. All the rates and temperature inside the reactor was uniform, right? So that's why we were able to write the only two equations. But in case of a distillation column, we have every tray, we have change in compositions, right? So that's why we will have more than two equations. So the example that I wanted to, that is the purpose is basically two, is that the occurrence of more than two reactions, more than two equations, as well as the a different case where similar analysis can be done. And major important feature is that where is the source of nonlinear term that we typically have in case of distillation column. So can anyone comment, or can anyone tell us that what is the source of nonlinear term in case of distillation column? What do we think that that this particular feature, for example, in case of CSTR, we had understood that the reaction term is a nonlinear term because rate is a then also a function of temperature. So exponential E minus RT, so that term is basically the rate constant, one of the term in the rate constant. So that is the source of nonlinearity. So similarly, in case of distillation column, what do you think that there is also a nonlinear term, and we have to deal the equations in the similar manner that we had discussed in case of reactor.
Sir, we'll have energy balance. Obviously, there will be a nonlinear
Hmm. Energy balance, where it will be the nonlinear term exactly? See, let us start from the mass balance or mole balance at least. So we have F equals to L plus, sorry, F equals to bottom products, that is B amount, and the distillate, that is D. Hmm. We also know that I'm just saying this based on the, let's say, continuous under the condition steady state behavior manner. So when we have a steady state behavior, then we try to write the across each tray, basically liquid stream coming from bottom tray and going up, and then again vapor stream coming from top tray and going down. So there we don't have any nonlinear term. Okay. Now in case of energy, it is basically the enthalpy, enthalpy, which is Cp delta T and mCp delta T, basically in that sense. So there also and Cp values, these are basically constant we consider. So not much variations, not much variations. So here our major variables or state variables, if we call it as state variables, are basically temperature and compositions, that is the percentage purity or the basically mole fractions that you talk about. So just think of that the where is the source of nonlinear term, and basically in the energy balance we are not um, we do not have any nonlinear term actually. So where could be the source of the nonlinear term? Is it lying on mass balance equations, or is it lying to somewhere else? Just think of little bit more. So we have our mole fractions present in liquid, mole fractions of more volatile component present in vapor. So we have Y at several, or Y changing from tray 1 to tray N, and X also changing from tray 1 to tray N. So I'm just giving the hints. So can you identify where is the nonlinear term? Who will tell it? Shraman, Pal?
Yes, sir.
Can you think of that where could be the source of nonlinear term?
The relation between the two mole fractions in each tray would be
What relation? Yes, you are there, but what relations? Mole fraction between what? Between what and what?
one component's vapor composition and the liquid composition.
Yes, so what is that relation called? Or what is the name of that relation? Yes, you are there. Just tell the relation's name?
Not sure, sir.
But you got it correctly. It is due to that relative volatility equations, right? Y equals to alpha x by 1 plus alpha minus 1 into x. So this is basically vapor liquid equilibrium relation. So in general, I was looking for that name, that what relations or what equations. So over the case or over this example, you have this nonlinear term, and this will again this can lead to a case where you may occur or may not also occur the multiple steady state, but at least one can do a similar calculations or analysis that we had discussed for reactor case. Only thing is that you will have more complicated case because there is more than two equations actually, because across each tray you have to write the equations. You have to write the equations, then you have to plug in the substitute the y so that you have x with you, and then your state variables are basically x and as well as temperature, and then over these relations you can again substitute back and get the y. So just let us at least qualitatively without going or solving step by stage by stage, or actually instead of having the detailed calculations, let us try to understand the qualitatively the plot. So what we have here is some descriptions or some assumptions are made, the one typically we do in the uh, case of design of column, but also here thing are that at each tray you have liquid hold up and vapor hold up. So we generally assume that this amount to be the constant, that does not change, but more rigorous model would be to have them as varying component. So but that will lead to more variables, and it will have more, it will create more complexity. So by assuming this constant hold up of liquid on each tray, we do not lose any informations. We are that's why these assumptions are actually considered. So typically this is the case, and we generally write the change in with respect to the so basically the derivative, first derivative of uh, liquid composition, so x dot n, so that actually refers to the change in compositions of liquid in the liquid stream. So this x and y are with respect to more volatile components, so these equations we can write. So across condenser, across tray above the feed level or feed flow, on the feed flow or below the feed flow. So total we can write as many equations as many tree, including the reboiler and condenser. So these are the nature of equations which you will be able to understand. It is basically the species balance equations of across all the tray, and this M are nothing but the liquid hold up, so the amount present in the liquid basically. So that is why it is or basically the mass or mole flow that is going in. So accumulation term equals to in minus out. In that way we have written all the balances, and then we can substitute the y in the form of x, and you will have the nonlinearity introduced across all the equations. Okay, so then what we do, we again can take up this linearization task, the one we did for reactor case, so that variations across the steady state point where xn could be one of the critical point or equilibrium point, and if the variation is small we can write the Taylor series expansion. So there in case of as we have seen in yesterday, that it is basically that example, or remember that this we were writing that this is a basically linear combination of some constant a into delta xt and v plus delta u. So x and u are basically input. So this, if you remember, then we discussed this yesterday. So this linear combination we can write. So in the similar approach, we can also make this, and let us now see what are the terms that is present in Z. So Z will contain, so there were total 16 tray, okay, so including the reboiler and condenser there were 16 tray. So across each tray we can have this x1t minus x bar at steady state. So basically this is a steady state composition across each tray, and this is basically the deviation variable and the change, the time derivative. So similar to this. And then we have one more relations, which is basically y is related to the z, because z gives us the liquid composition changing as a matter of this unsteady behavior or transient behavior. So the different term that are contained in the A matrix and B matrix are evaluated, and those are nothing but the coefficients of the first derivative or the Jacobian, and calculated at the steady state point. Only thing is that you have here more equations and the elements are large, so it is basically 16 by I think 2 by 16, or yeah, basically two variable or two state variables, and 16 trays, so 16 equations. So it is basically 16 by 2 column, two sides, the matrix size. So accordingly you will have the eigenvalues, and you will see that how is the behavior. So as one another important point I would like to make is that the concept of this linearization or is basically required. The deviation variable perturbation of the this delta amount and their time variant features or the transient behavior of that deviation variable is actually nothing but forms the input to the controller. So if we want to control because some disturbance can occur. Now what are the sources of disturbance? It can be feed flow rate or it can be feed compositions. So these are the major source of the what is called disturbance introduced in the uh, system. So suppose it was running smoothly, but suddenly we increase the flow rate or change the compositions. So that will affect all the other trays, and there will be a transient behavior. So basically this, if we have a controller action available with us, the smaller variations or deviations it can understand, and accordingly it will again restore back the column conditions. So this linearization has not only the advantage of understanding what is that stable point or unstable point, but also it is required for the controller design. So these are the elements of the matrix A, and you can see that similarly we can also do it for matrix B and C, and these are all written for symbolically because there are more than two equations. So for all the trays we have written down, and you can see that coefficients, right? Coefficients, this small a are nothing but the coefficients or elements in that big A matrix. So in this way, if you do the analysis and then basically qualitatively, if you look at the plot, you will see that this is the case, that x and y actually changes and across each tray, and this is basically the results that we see. That across all the trays, so xb is basically the desired bottom compositions and xd is basically desired top compositions, overhead compositions, and this is how they actually changes with respect to time. So more or less all that across all the tray it reaches the steady state, and this part is basically the transient part, or at least up to this part you can call. So qualitatively, we can see this what is called results. Of course, this has been obtained by solving the equations and integrating it over with respect to time. And this is the basically purity of the distillate product. That means the top overhead product across all the tray. So Similarly, you can also do the y. So this example I also wanted to give is that distillation column can also introduce nonlinearity, and it is also essential to analyze by doing the linearization to know or characterize about the steady state point as well as the that forms the feed into the controller. So the behavior of delta xt or the deviation variable, so that actually is the input. So basically in the controller you have the several of the eigenvalues, the lambda as a controller tuning parameter. So the calculation of lambda is essential. Uh, and this is the way, and we had looked at two different examples. So you have any questions over this or over uh, the cases that we had discussed about this concept? Any questions over this particular topic? You have to continue your reading so that you don't miss or you don't uh, fall. So the discussions that we are having in each class are are important. So this is basically your syllabus, whatever we will call in the class or discuss in the class. Based on that, you will be evaluated. So don't miss the class, or if you have not attended, but go through the recording part as well. So you may expect not only the numerical questions or modeling problem as in a proper question, but also some objective or short answer type questions. Maybe one line answer or MCQ uh, uh, can also be given. You have to read it and understand also. So both mathematical part as well as the understanding part are required. So don't miss these discussions. Okay, so if there are no questions on this topic, then at least we move towards a little bit different but related, and then we will take up ordinary differential equation applications. Okay, so one another example, or rather it is basically kind of, you can consider it to be a ordinary differential equation example, but since we had looked at some unsteady phenomena or the transient behavior of reactor, and we can also see that when we start a CSTR, though basically isothermal mode, we can also do it for non-isothermal. In fact, we should do it for non-isothermal. But when we actually start a CSTR, then what is the time that it takes to go to the steady state behavior or concentrations or conversions at the end of reactor when it is operated at steady condition? Then we have a conversions at the end of reactor or concentration CA out. CA out or XA out. So so that steady condition or steady concentration conversion. So what is the time that it requires to reach to that steady concentrations, right? So that is another kind of questions. Of course, we can consider it to be a numerical problem, but consider it to be from more physical perspective is that because we are running the CSTR at usually steady state condition, suppose it has not been started, or if it has not been or it is on the verge of going to shutdown, because in industry we oftentimes go for shutdown or startup of let's say distillation column or the FCC reactor. So this knowledge we must have, that when we again start the reactor or when we again start the unit of process, how what is the time that it requires to reach to the steady state again. So this can be quickly calculated for different order reactions. So this I will not elaborate much because this is common or standard calculations which you will be able to understand. So this has been done for first order, zero order, and second order reaction. So go through it. This is just some simple integration has been done, and what you can expect is that. This basically time required to reach 95% of its steady state conversions, that one can ask to calculate, or time required to reach 99% of the steady state conversions that it requires to. So this calculations is required. So go through it, and if there are some mistakes or something is missing in this PDF documents, then you highlight me. Just go through this derivation and see if you can get this kind of expressions where you have just basically CA and time. So this plot you can also make. And long enough time, CA is basically the what we are expecting at steady state conversion concentration. So CA out, right? So this is basically the equations for first order. Similarly, we can also have a zero order reactions. So one may ask that what is the time it takes to reach to the final steady state, or what is the steady state value of the concentration or conversion, and what is the time required to reach the 95%. So these are basically the um, related questions that we can ask, or related thing that we have to consider. So different order reactions, it is mentioned. For second order, it will be more complicated because of the several terms introduced, and the equations is not straightforward differential equations, but you go through it and I'm sure that you will understand these features. You got it? Got this discussion? Yes, no?
Yes, sir.
Okay. Okay, so now let us go to the different examples from just ordinary differential equations, where we will start with very simple examples, and then we will complicate our case, and consequently we will discuss. So what are the different agenda on this topic? So previously we looked at linear algebraic, then we looked at nonlinear algebraic, and particularly we discussed about multiple steady states. And then we also had looked at linearization or part, and the stability of the steady states, different examples. Now what we are more interested is the actually when we have several ODEs or system of ODEs, and in particular we will take up the case where we have to solve either isothermally or non-isothermally in a PFR. Typically the plug flow reactor case will be more dealing with, because this leads to ordinary differential equations. When it is operated at steady state condition, then we have the concentrations which actually varies along Z, the length of the reactor. Those actually leads to ordinary differential equations, and we can have generally initial value problem we will be more interested to look at. And further is that when these kind of equations we will also have, and then at the end we will look at what are the different kind of this concept of basically stiffness. So stiff differential equations and their physical meaning, and how to go for solutions of stiff differential equations. So these are basically the agenda in this particular topic, where 2-3 cases we'll be discussing, we'll be showing the MATLAB applications, and then we will in particular we'll highlight the concept of stiffness, and in MATLAB how does it change, and what analysis, again sort of analysis we have to do, that we can understand. So this start saying this, let us start, or let us see what are the different cases that we can consider. So typically these are some concepts lines, or just you can read, and which we all aware more or less, that this, in case of PFR, these equations we can write. If you do the derivation, or starting from the cell balance, or the differential element, the small delta z, if you carry out that balance, mole balance, then you will typically have this kind of expressions, where rate is a function of, uh, or you can express the rate as like this. So this basically forms a ODE system of ODE if it is more than one component. Then it is a function of, and then based on some initial condition, we can basically calculate the conversion concentration with respect to the z. It's basically a steady state PFR. But if it is a that means it's a homogeneous reactions are occurring, no catalyst, no solid part. So if it is a catalytic reactor, then the rate is basically changed, and we have, instead of R, we have R dashed, where rho b is basically expressed in terms of mass of catalyst. So in case of homogeneous, as you all know, the reaction rate is expressed with respect to per unit reactor volume, or the volume of the fluid. Or if it is a catalytic reactor, then basically it is a per unit mass of the catalyst. So that expression is sometimes not or usually that we find in as R equal to KCA, the first order, or KCACB. So in case of heterogeneous or catalytic reactions, these rate expressions are different. So we will at least see the nature of these equations and how we can solve them in MATLAB using several ODE solvers, several ODE solver. So typically this similar in case of batch reactor, you can also see the this sort of differential equations. So this is very common. I mean, this in chemical engineering applications, not only the reactor or different, but other cases different. You will see that you more or less you have to solve ordinary differential equation, either one or more. So this will be kind of routine applications, or routinely you have to do it. So typically there are ways to write the MATLAB program, which more or less you know it. Still, I have written it for the sake of completeness, and which you can go through. Or so as we also discussed in previous lectures, that typically there are 2-3 steps that you need to follow in order to write the MATLAB files. One is the called function file, where you have the right hand side of the differential equation is expressed, or any algebraic relations, and there is something called the left hand side or main file, or where you are actually solving it and getting the values evaluated. So this part, if it evaluates, then this at the rate or RHS, that is the function file that it calls. So based on the input range or initial values, it starts evaluating all the intermediate values, and then it shows the final values in the main file. So through this plot option. Okay, so these are the two simple just MATLAB files that we have written it for this case. Now if it is more than one, then what you have to do, we have to just add up continuously the different so it will be a basically row vector, and you have more than one lines, so accordingly your modifications will be there in the MATLAB files. Okay, so typically in this case of ordinary differential equations, we use ODE 45. So do you have any idea about what algorithm is used in ODE45? At least let me see if you know it. So what is the algorithm that we use in ODE45? Ankit Verma. Adrija Roy.
I don't know, sir.
Acha. Anyone? Who will tell this answer? Who know this? This ODE45 is based on which algorithm or numerical technique? Rather, algorithm means like which numerical technique? What are the different integration technique in numerical methods? Let me put it in this way. What are the different integration methods that you have learned in numerical method course?
So some of them are Runge-Kutta, Adam.
Yes, correct. So you know at least, right? So Runge-Kutta fourth order. Have you studied Runge-Kutta fourth order? Typically
Yes,
RK4 method, very common. Right. So Runge-Kutta fourth order, and basically the error turn. So there are slight variations of Runge-Kutta fourth order and Runge-Kutta fourth and 5. So basically 45 we call 45, but it is basically Runge-Kutta fourth order method, ODE45. ODE45 is used in case of typically we don't run into problem the convergence time and the calculation time, the time elapsed for the integration, and typically if the equations are more or less non-stiff in nature, we don't run into problem using ODE45. There are other ODE solver technique which are based on some other algorithm, let's say implicit. So ODE45 or RK method, fourth order, they are based on Euler technique, right? Explicit Euler. But there are other methods which are also based on implicit Euler. For example, Adams Moulton method, I think, or Geer's method, if I'm not mistaken. So, but those are a part of the numerical technique. So we will not discuss about the technique, but we will see where we can use them. More or less, we will use ODE45, but somewhere we may not be using this because that is not a efficient algorithm for the problems that we will have little later. We will show some with examples. So those are basically stiff problem. Maybe we will in particular discuss that in the next class, but today we will at least start with different cases where we can use very efficiently the ODE45 method. Okay, so some simple MATLAB lines you will be more familiar to see it is that there are two ways we can pass some parameters. So either we can use that features present in MATLAB called we can write as global. So that we have to just recognize the code, or we have to just tell the system that this parameter will be used in the functions calculations, and that is we will define in the main file. Right? So this one way we can pass it, or we can also pass the parameter not by writing global, but by using it as a one arguments. We pass the arguments in the main equations, that is, or main lines that we use for calling the solver to solve it or execute it. And if we are passing the parameter here, we have to also pass the parameter here, because this y dot, that means the left hand side, this y, several of the y's are calculated by the function file or function that we are writing. So here it was just minus ky d by dt. So, but there can be many. But k is now a passing parameter where k can vary, and either way we can write it as either this global way of defining it, or we can just pass the parameter as arguments, one more arguments in the function handle. So this time sometime called function handle, because here we can also change the relative tolerance. So based on the error criteria, so we can change with the help of options. This is basically the initial conditions. This is the what is called the span of integration, the time that you are taking, and we don't have to particularly give the step size, because we invariably this using some numerical technique where it inherently calculates the step size. You can see the step size that it takes. Also, I think you can change the step size by writing the options. That part I've not looked at, but I believe that there is a possibility that you can also do some step size change as your own, but that one has to see. But anyways, typically the thing that is available in MATLAB, just by calling this ODE45 and solving a system of equations or a single ordinary differential equation based on these input parameters like the time span, the initial values, and the relative tolerance if you want to change it. So you can easily get the variations, the distribution of your maybe temperature or concentrations or mole fractions with respect to time. So simple lines can be very effective, and just we can get the results, the desired results. Okay, so now we will have one case which is basically the isothermal PFR. Isothermal PFR. So this reaction stoichiometry that we have written, 2A going to P. So this is just one customary examples. There can be more. It looks more or less a simple example, but it can be similar in nature, and we can have several other equations or based on stoichiometries. So where we are having some equimolar components, or the A and C. So C is basically inert. C is basically inert. In several reactions, we actually use inert. In industrially different gas phase reactions that we use, we oftentimes use we call them as diluent or inert, right? So that has several advantages. So here we are taking a case of isothermal PFR. We are not trying to make the system more complicated by introducing non-isothermal, but if it is there in non-isothermal, you will have the temperature line. But it is in case of PFR, as we have said, these are all operated on steady state conditions. So we are looking at a steady state isothermal or non-isothermal PFR. And these are the equations that we earlier also had shown you, that this is the form of expressions. And for the several what is called the species, that is A, B, and C, we can write the equations. Now, since C is an inert, so there will be no change in the C. So this is basically the 0, and for A and B, we can write it, right? So based on the initial conditions, we can easily integrate, and some values of the velocity of the fluid or the liquid stream, and total length of the PFR is also given. Rate constant is also given, and we have to just write the M file, the function file, and the main file, and just solve for different concentrations, right? So this I have not, I think I have written the code, or I have not. I have not. So these are just simple lines. You don't need to. I have not written it, but since the some previous example based on which you can easily write it and solve it for CSE, BCC. Now here things can be a little bit more interesting, because here we have assumed that there is no change in density. For example, let's say if it is a gas phase isothermal reactions, and we are allowing the volume change, we are allowing that means the volumetric flow rate and the inlet of the PFR and the outlet, it is not the same. It actually changes. So volume expansion we are considering or taking into consideration. and that epsilon term. So that can be introduced. So if we introduce that term, then you have to incorporate that, and accordingly your conversions or other concentrations at the end of the PFR or at different lengths will vary. So here we have not considered that, but that can also be considered. So you should be able to do that, and by changing the lines and equations little bit, because that volume variations has to be considered. So you will not, so accordingly you have to maybe start it as exactly df dv in that formation. So in this way you, because when we describe F as the molar flow rate, we consider that V into Ca, and then we take out that sorry, volumetric flow rate out. So instead of that, we will not take out, because this also will vary along with this because of the volume change considerations. So that part you should be keeping in mind, that this V also is now within that integration. So we are not assuming it to be constant. So in that way, we do not arrive at these equations, but we start it with directly with this, and based on this we can consider and write the equation. So instead of CA, CBCC, we may be interested to write FA, FB, FC in terms of molar flow rate. One might ask you to that what is the conversions at the end of the PFR. So from the plot or from the data, you should be able to calculate the conversions, because you know the initial amount of moles or molar concentrations, and you will know the at the end of the reactor what is Ca. So in this case also, in case of the volume variations consideration, you should be able to calculate the conversion as in terms of F. So FA out, FA in minus FA out by FA in, right? So here, when there will be volume variation consideration is there, you do not consider to the right in terms of concentrations, rather molar flow rate. So remember these things in mind. This can be sometimes tricky. Sometimes we just do not read the questions carefully, but we start again using the same expressions. But one has to be very careful about what starting expressions or starting equations would be looking like. So reading the questions very carefully. Whenever we do this kind of calculations, we oftentimes ignore the physical side or the systems, what the systems is representing to us. So that has to be, one has to be very careful over those things. Now, one more examples is with respect to this non-isothermal CSTR, as I was, sorry, CSTR, non-isothermal PFR, and typically this sulfur dioxide oxidations to form SO3, because this is one important steps in sulfuric acid manufacturing. So this sulfur dioxide oxidation to form sulfur trioxide is one of the major industrial reactions that is happen in PFR, and and this is a catalytic reactions. So as I said, that reaction rate R dash is something different. It does not look like to be very simple expressions. Because of this is a catalytic reactions, so adsorption and desorption will be there. So adsorption equilibrium constant, desorption equilibrium constant, these are all there. So this kind of expressions is you can understand and see the complexity involved in it. Again, as I said, that in case of non-isothermal, we will have a heat removal term. We will also have some heat generation term, and due to the variations across the length of the reactor, so this dt dz term will always be there, and this is we also have written as dx dz. So this though the final expressions, the final formulated expressions are written here, the differential equations, but one can start it based on reading the questions and writing the different terms that are present, because at this stage I guess you should be able to write the balance equation from scratch, be it CSTR or be it PFR, isn't it? Will you not be able to write the balance equations in case of PFR, non-isothermal PFR, steady state, or unsteady state CSTR, non-isothermal? Yes or no? Rahul Kumawat, Shaksham Arya, Muhammad Athar, Sahil Bairagi, no one is responding. Shivans Raj, okay, no problem. So this these are this has to be solved based on the initial conditions. So temperature and conversions at T equals to 0 are given, and these are additional relations of this because K1 and K2 has to be provided, and they are also function of temperature because these are equilibrium constant, adsorption equilibrium constant, and this is the overall this equilibrium reaction equilibrium constant. So this can be written, and this can be solved. So I have also written additionally for your reference the different MATLAB lines which you can directly implement, and you can see the plot results. Okay, so you can see the temperature and conversions across the axial positions, that is the basically Z. So both temperature as well as conversions with respect to the Z, the length of reactor, you can plot. So you may get some optimum or something. So this sort of complete calculations along with the results are also required, and then you will be able to understand and relate the phenomena that are occurring in the reactor and the temperature or conversions or concentration variations. So we do not just look the problem to be just sort of a mathematical problem, but also this sort of results plotting will actually increase our understanding about the problem, the phenomena or the processes that are actually happening inside the system, right? So these two are essential, that we not only write the model equations or we just not only solve it, but also we plot it and see whether it makes sense, whether it is meaningful or not. So this has to be kept in mind, and I'm sure that you are able to write different MATLAB lines, but still for all your sake of reference and benefit, I have written down the script file as well as M file. So this is the where in the evaluation section or in main you will execute these lines to calculate the y, where the y is basically a column vector, sorry, row vector, where temperature and conversions are there, and based on this we actually are able to plot the data. So practice this. I mean, this will be required not only for your exam, but in the term project that you will be doing. So one or two different particular case studies. So they have to be considered, and you have to solve it using MATLAB. So our TAs are also there, Deepak, Sunil, and Rushikesh. So they will assist you in in case of if you face any difficulty over those term projects in terms of modeling the problem and writing the and simulating the results. So this MATLAB lines, you start practicing, it will benefit you, and in case of any queries you can inform me later. So just I'll introduce and then I'll conclude the class. Is that this particular topic is important, and the detailed analysis or results we will discuss in the next class. So one more applications in case of when we have a mass transfer also occurring inside the reactor. So till now we had looked at cases where we only had reactors, just chemical reactors, whether it is a homogeneous or heterogeneous, but could be the operation as isothermal case or non-isothermal case, but they may they may be solved over the system, and they may actually form several ODEs, and we can solve them as per standard routing, standard subrouting. But when we have a mass transfer also involved in the process, then it appears that the concentration based on which we calculate the rate at that particular point, or typically the way we write. So Ca is basically the bulk concentration, we oftentimes are understood by the notation, but Cas is basically the surface concentration, or to the concentration that is not at the bulk. So when we say that surface, then that means there are some something is there on this side, maybe let's say liquid or gas, and then you are encountering a different phase, which could be a solid phase. So one application is that you have a catalytic reactor where walls are coated with catalyst, right? So this is a PFR, but you have the catalyst material coated on the wall. So in that case, your reaction is happening not in this fluid portion, not in this straight pipe or in the fluid element, but it is occurring on the surface of the catalyst. So main reaction is happening on the wall or catalyst site or catalyst surface. So that means concentrations at the surface is important, and that's why we have written it like this. If you just see the reaction stoichiometry, it is basically 2A going to be the same example we are considering, but now we are considering with respect to the mass transfer limitations. So this particular case we will have to solve, and by ODE, but we have to incorporate one more equilibrium, one more algebraic relations, because CAS, these surface concentrations or the solid concentrations are not measurable. They are not measurable quantity, but theoretically or in principle, this is actually the concentrations that based on which we are calculating the rate. And that's why the Ca is actually changing along Z, and across the end of the reactor we are getting some final concentrations. So this algebraic relation is one more features, or one more mass balance relating the mass transfer. So what we consider is the rate of mass transfer from the bulk to the surface is equals to the rate of reactions by the surface catalyst, or the so the rate at which the species goes to, or the number of moles of that particular component, that is A, reaches the same rate it is basically consumed by the reactions. So the unit wise it has to be consistent, and this way we can also calculate CAS, because KM, KAS, these are actually given. Km in not in the form of Km but Km into A. So this is basically the mass transfer coefficients, and the A is the interfacial area. So these two together are typically given, and so we can calculate CAS, and that we can plug in and we can solve the differential equations. So this we will see in the next class in more detailed manner, and the cases for this kind of and we will also compare vis-a-vis the different mass transfer or without mass transfer. So this we will again take up in the next class, and I would suggest that you try to read a particular topic, or at least get some idea or knowledge about stiff equations. Okay, what is stiff differential equations and what are the different so maybe I write the question here. So what is stiff differential equation, what is stiff ODE, and what are the solvers. The second is solver for stiff ODE. So these two questions you just try to go through it and have some prior information available with you, so that we can discuss better in the next class, because next class will be mainly devoted on this stiff ODE applications and the implications or physical understanding that we can get from this equation, or by just looking at the nature of the equations, whether we can say that what kind of solver we have to use. For example, sometimes we get several ODEs where there are some due to nonlinear feature, we oftentimes just plug in the ODE45, but we run into problem. We say that it is not working, but maybe we are not choosing the right solver for that system of ODEs where there could be a stiff ODE. So this sort of analysis or understanding we have to make very clear. So this will be the form or basis of the discussion in the next class. So what assignments today, there will be no assignment, but what I can ask to my TAs to prepare the question that I already sent to them. So based on that, I will send you the assignment, which will be based on that propylene glycol problem and looking at the multiple steady states as well as the analysis by eigenvalue or method, or in that the one that we discussed by doing linearization. So the nature of the steady states, so by that means the stability, whether they are stable or unstable. So that will be the your assignment 2, and today is the deadline for your assignment 1. So typically just since we have little bit more time, so we can just comment the evaluation part or the weightage part. So there will be 2 assignments. Till now we have given 1, and there will be 1 assignment which I'll be giving next couple of days. So these 2 assignments will be there. Then there will be a term project which you have to do in the 1 or 2 weeks span. So in the month of February. So that term project will be based on some applications of combining this algebraic or ODE or PDE. So there will be case studies where the system of equations that we have to deal with to get the final answer is a combination of several equations, could be algebraic or nonlinear, linear. So right now we are going case by case, but finally in the term project you will have a problem where you have to deal with a combination of these cases, individual cases. So then the turn project will be there. After that we will have a short mid-sem which will be occurring on during the mid-sem window in the February, and then we will have at the end of the semester, that is final exam. So after my part, Professor Varanasi will be continuing his part of from February 27th or 28th or that week onwards, and before that I will be continuing. So these are basically the plans for the evaluation part. So any questions over this evaluation features or the weightage in the class or weightage in the marks? because this is very important. This is a part of your evaluation. So if you have any question, you can ask me now. Okay, no question. If not, then we call it a day and we again meet in the next class. So Sunil, Deepak and Rushikesh, you try to send me the assignment questions by discussing with you and frame it in the Word file and send it to me by Thursday. Or when today is what, Tuesday, na? So by Thursday you send me the question. All right.
Yes, sir.
Okay, then thank you the class. We meet again next week Monday.
Thank you, sir.